Welcome to the Hodja on Everything, the Space. Chapter 4 Stars Died for You. In the previous episode, we discovered that looking deeper into space also means looking further back in time. The night sky, we learned, is not a live broadcast, but an immense historical archive. Every telescope is a time machine, every galaxy a different chapter in cosmic history, and every beam of light a message sent long before humanity ever looked up. Today, we continue that journey, but instead of exploring galaxies, we turn our attention to the objects that make galaxies shine. Stars illuminate our skies, warm our planets, and quietly govern the chemistry of everything around us. They also happen to be remarkably dramatic creatures. If galaxies are cities, then stars are their citizens. Every citizen eventually reaches retirement, although stars tend to make considerably more noise about it. Every star begins life inside an enormous cloud of gas and dust known as a nebula. These clouds drift through space for millions of years until gravity slowly gathers the material together. As more gas falls inward, pressure and temperature rise until the center becomes unimaginably hot. Eventually, hydrogen atoms begin fusing into helium, releasing extraordinary amounts of energy. At that precise moment, a star is born. The universe, it turns out, has no maternity ward. It simply compresses gas until it ignites. Our own sun was born this way around 4.5 billion years ago, and for most of its existence it has been a remarkably ordinary star. Every second it converts hundreds of millions of tons of hydrogen into helium, producing the light and heat that make life on Earth possible. We often think of stars as permanent features of the universe, but they are really enormous nuclear power stations with a limited supply of fuel. Like every machine ever built, they cannot keep running forever. Stars, rather like people, have careers. Some work quietly for tens or even hundreds of billions of years, while others burn through life astonishingly quickly. The larger the star, the shorter its life tends to be. It sounds completely backwards until you remember that the biggest engines also burn through their fuel the fastest. Massive stars seem to follow the philosophy of living every day as though it were Friday evening. They burn through their fuel at astonishing speed, enjoying brilliant but surprisingly brief lives. The universe, it seems, rewards moderation more than enthusiasm. Eventually, however, every star faces exactly the same problem. It begins to run out of fuel. Humans often respond to midlife crises by buying sports cars or taking unexpected holidays. Stars become red giants. Frankly, expanding until you swallow your nearest planets seems a rather dramatic way of processing your emotions. Around 5 billion years from now, our own sun will enter exactly this phase. Mercury will disappear, Venus almost certainly will, and Earth's future is complicated. Fortunately, none of us has a calendar that extends quite that far. When the sun finally sheds its outer layers, all that remains will be an intensely hot stellar core known as a white dwarf. I have always thought that white dwarf sounds less like an astronomical object and more like the eighth member of Snow White's support group. For stars roughly the size of our sun, that quiet retirement marks the end of the story. For larger stars, however, retirement is where the real excitement begins. Massive stars spend their entire lives racing through their fuel supplies. While smaller stars are content producing helium for billions of years, the giants refuse to stop there. They continue fusing heavier and heavier elements. Helium becomes carbon, carbon becomes oxygen, oxygen becomes silicon, and the chain continues until the star eventually begins producing iron. This is where the universe politely says, "Thank you, that will do." Iron is an unusually stubborn element. Fusing it no longer produces energy. Instead, it consumes it. The nuclear furnace that has supported the star for millions of years suddenly begins to fail. Gravity, which has patiently waited throughout the star's entire life for an opportunity to take control again, wastes absolutely no time. The core collapses in a fraction of a second. The outer layers follow, then rebound in one of the most violent explosions the universe has ever witnessed. A supernova is so bright that for a brief moment, a single dying star can outshine an entire galaxy containing hundreds of billions of other stars. Imagine spending 10 million years behaving like a perfectly respectable star, only to end your career by becoming one of the brightest explosions in the observable universe. That is commitment to making an unforgettable exit. Yet the explosion itself is not the most remarkable part. It is what the explosion creates. Many of the heaviest elements require the extraordinary conditions created during a supernova. Your wedding ring therefore experienced considerably more drama than your wedding hopefully ever will. The calcium in your bones, the iron flowing through your blood, and many of the heavier elements around you owe their existence to generations of dying stars. People often say they are worth their weight in gold. Technically, you are worth your weight in supernovae. Humans like to congratulate themselves on inventing recycling. We carefully separate paper, plastic, and glass into different bins and feel rather pleased with our commitment to environmental responsibility. The universe has been recycling entire stars for nearly 14 billion years without asking anyone to rinse the containers first. Every carbon atom in your body once belonged to something else. The universe has never believed in buying new materials. It simply keeps rearranging the old ones into increasingly interesting combinations. In a very literal sense, every medical examination is also an inspection of stellar archaeology. Not every supernova leaves the same legacy behind. Some produce one of the strangest objects in the known universe, a neutron star. Imagine taking more mass than our sun contains and compressing it into a sphere barely 20 kilometers across. Matter becomes so unimaginably dense that electrons and protons merge into neutrons. A single teaspoon of neutron star material would weigh billions of tons, which is generally considered rather poor table etiquette. And if the original star was even more massive still, gravity refuses to stop there. Something even stranger begins to emerge. If gravity continues squeezing matter beyond the limits of a neutron star, the result is a black hole. Despite the name, it is not really a hole. It is a region where escape from gravity is impossible. Few objects in science have attracted more myths, documentaries, and dramatic background music than these extraordinary remnants. Black holes have perhaps the worst public relations department in the entire universe. Every documentary introduces them by saying, they swallow everything. Nobody mentions that they are simply following gravity a little too enthusiastically. They are not cosmic vacuum cleaners wandering through space looking for unsuspecting planets. If our sun were magically replaced by a black hole with exactly the same mass, the Earth would continue orbiting almost exactly as it does today. We would have rather more serious lighting problems, admittedly, but gravity itself would barely notice the difference. The truly remarkable feature of a black hole is its event horizon. Think of it as the last motorway exit before an exceptionally long journey. Miss it, and there is no convenient place to turn around. Beyond that invisible boundary, every possible path leads inward. Even light, the fastest traveler in the universe, cannot escape. That is why black holes appear black. Einstein would probably have smiled politely and reminded us that this too is just geometry. As though exploding stars and black holes were not strange enough, physics still has one final surprise waiting for us. One of the strangest predictions in physics turned out to be true before anyone had actually seen it. Every ordinary particle appears to have an opposite twin known as antimatter. Matter and antimatter are almost identical, except that their electric charges are reversed. When they meet, both disappear in a brilliant flash of energy. Matter and antimatter have the least successful blind date in the history of the universe. If you ever wanted proof that some relationships are not meant to last, physics has already run the experiment. Why our universe contains so much ordinary matter and so little antimatter remains one of the greatest unsolved mysteries in modern science. Had the two existed in exactly equal quantities after the Big Bang, they would have annihilated one another almost completely, leaving behind little more than light. Quite literally, the fact that you exist is evidence that something, somewhere, tipped the balance. Perhaps that brings us to the most extraordinary idea of today's journey. When you look into a mirror, you are looking at recycled stardust. The iron in your blood, the calcium in your bones, and much of the matter that makes you who you are were forged inside stars that lived and died billions of years before Earth existed. Some ended quietly as white dwarfs. Others became neutron stars or black holes. Every one of them changed the universe for whatever came next. Stars died for you. In the next episode, we will zoom in once again, leaving individual stars behind to explore the remarkable variety of planetary systems that surround them. We will visit our own solar system, discover thousands of distant exoplanets, and ask one of humanity's oldest questions: what makes a world capable of supporting life? As it turns out, being in the right place at the right time is not just good advice for people, it is also remarkably useful for planets. This concludes Chapter 4 of The Space. Stars died for you. Thanks for listening. See you in the next episode.